Hey, it's showtime. Welcome to Chill Skills Sporlan Tech Talks. The topic for this episode is what is refrigeration? This happens to be part one. Thank you to everyone that's joined us today. This is the 11th, if I recall correctly, in a series of presentations that deals with supermarket refrigeration. And I'm able to count that height without taking my shoes off, at least so far.
That's excellent.
Yeah.
I'm happy to hear that.
Thank you. While it does not necessarily follow the agenda of the old supermarket seminars, it is an important aspect of refrigeration science and it is very applicable to the air conditioning side of things as well. Today, you'll learn why things become cool, cold, or frozen by simply transferring heat. Here's a shameless promotion for the next webinars. Later in September on the 17th, we'll follow the schedule of the ongoing supermarket series and we will continue our discussion on methods of temperature control with electric evaporator pressure regulators. Then to make things ever more interesting, in early October, we're doing another webinar. It'll be part 2 of this What is Refrigeration series. This webinar would be perfect for anyone who wants a better understanding of the vapor compression refrigeration cycle, or for someone simply wanting a review of the basic concepts. We'll do part 2 on October 1st. Now, part 2 will really kind of pull everything together. Good bet you'll have questions that we'll probably answer when you listen to part 2. So just hang in there and join us for these upcoming webinars. Here are a few instructions. If the speaker on your computer doesn't work, you can simply dial in with your phone. There should be a dial-in number somewhere on the invitation that you originally received for the webinar, but here it is on the slide in case you don't have it handy. As we move along and you have questions, you can type those questions into the Q&A window. We'll try to answer some of them in this live format. Oftentimes we run out of time to deal with them all, so don't feel bad about that. We'll eventually post answers to the questions online. And again, we may very well answer your question during the course of the webinar itself. And just so you know, we're recording this, and should we run into any broadcasting problems today, you can always go back and listen to the recorded version. It'll appear first on Facebook Live, and then later on the Sporlan YouTube channel. Hello, I'm Jim Jansen, Senior Application Engineer for the Sporlan application team. That's me on the left. And joining me today is John Whithouse. John is the Senior Principal Engineer for the Sporlan Division. He's a published author, consultant, and as I have said many times in the past, all-around extra smart guy. All this means John is a big deal around here, and we're really excited to have him with us today. Why don't you say hi to everybody, John?
Good afternoon, everyone. Oh, that wasn't really high, but that's even better.
That's even better. I really feel the need to thank one of our good old friends, Gene Ziegler. He's one of our former colleagues, and he really needs some credit because he helped us craft this original presentation. And if you're out there listening, Gene, here's to you. Phyllis is back in the room today. She's our marketing communications director. She tells us what to do and when to do it. And every once in a while, we even listen to her. John, you know, I got to say, I've always admired your mustache.
Well, thank you, Jim.
Would you mind if I just borrowed it from you for a while? You know, you're going to have
Sure.
to do without it. You okay with that? If you have any follow-up questions, notice I didn't let you respond to that. You may contact us by email.
I did actually notice that.
Yeah, did you? Mm-hmm. svdtechsupport@parker.com, or you can always call us because we've got people here that'll answer the phone. 636-239-1111. We'll share this information with you again. Mechanical refrigeration systems are valued for their ability to achieve temperatures below that of the immediate surroundings for everything from food storage to climate control. Temperature refers to the degree or intensity of heat present in a substance or object, especially as expressed according to a comparative scale and shown by a thermometer or perceived by the touch. When we say an object feels hot or cold, this means the temperature of the object is generally higher or lower relative to our body temperature. In the United States, that's the United States, we use the Fahrenheit scale thermometer. Using this scale, the temperature of water boiling at sea level is expressed as 212 degrees, and the temperature at which water freezes into ice is expressed as 32. This temperature scale was originally developed and named after a German physicist. You want to guess what his name was? It had Fahrenheit in it. Daniel G. Fahrenheit, who invented the mercury thermometer. In other parts of the world where metric measurements dominate, a thermometer scale referred to as a Celsius scale is commonly used. Using the Celsius scale, the temperature of water boiling at sea level is expressed as 100 degrees, and a temperature which it freezes as 0. This temperature scale was formerly known as the centigrade scale. It was renamed after a Swedish astronomer, Anders, come on, John, say it, Celsius, who invented the inverted form of this scale. That's right. Originally, 0 degrees was hotter than 100 degrees. Go figure. Now, refrigeration may seem simply like the act of transfer of heat from a given space to a refrigerating medium known as a refrigerant. The heat is then carried to a place where it may be rejected to the refrigerant and discarded and put to another useful purpose. And if that's simply all we had to talk about, John, we'd almost be done with this. You can see here the 4 main components in a refrigeration system: the compressor, the condenser, the metering device, and the evaporator. And here I'll use a little laser pointer to point those back out again. Suction line, discharge line, liquid line feeding the metering device, and then on into the evaporator. 4 main components.
4 main components.
And all we're doing is transferring heat from this space that we're trying to cool to the refrigerant, and then we're rejecting it by use of this condenser to a space where nobody cares if it exists. We need to define a few more terms in order to make sense of all of this. And one of those terms is simply pressure. Pressure is defined as a continuous physical force exerted on or against an object by something in contact with it. Sort of like, just like if you add air to a tire, the pressure increases. Pressure is usually further defined as force per unit of area. In the refrigeration industry, here in the United States and a few other locations, pressure is normally expressed in terms of pounds per square inch, or PSI. Atmospheric pressure is also called barometric pressure. And that's a force per unit area exerted by an atmospheric column or the entire body of air above a specified area. Atmospheric pressure can be measured using a Mercury Barometer, which measures the force exerted by the weight of air, displayed in inches of mercury, which is typically abbreviated as INHG. Now, John, how in the world do we get HG out of mercury?
Well, that's a great question, Jim. It comes from the Latin word hydrar euros, meaning silver water or liquid silver.
Oh, now, see, I told you all, John is one smart dude. Who would have known that? A mercury barometer can be constructed by inverting a glass tube closed at one end, approximately 3 feet long, and filled with mercury. And then you tip that over into a container of mercury. And as the glass tube is inverted, the level of mercury in the glass tube will try to run down into the mercury that's in the container, but all of it can't get out. When the glass tube is vertical, the mercury in the glass tube will fall to a level equivalent to approximately 760 millimeters or 29.92 inches in height at standard sea level. The space occupied at the top of the glass tube, void of mercury, will be in what's called a vacuum. The weight of the air at atmospheric conditions applied to the mercury in the container provides the force to maintain the level of mercury in the glass tube. As atmospheric conditions change, the level of the I have to learn how to talk again, John. The level of the mercury in the glass tube will rise or fall somewhat to account for the changes in air pressure. As the air pressure exerted on the mercury in the container increases, the mercury level in the tube will rise. As the air pressure exerted on the mercury in the container decreases, the mercury level in the tube will fall. Isn't that special? Now, standard sea level pressure equals 29.92 inches or 760 millimeters of mercury. The mercury in the column of a barometer has weight and counteracts the atmospheric pressure of 14.7 psi at standard conditions. Now, John, you know, I think that number is we've taken some liberties with that. I think it's rounded off. That number is actually, isn't it something a little more precise than that?
If we want to be really precise, we could say that it's 14.696 PSI.
Oh gosh, that's too complicated for me. 14.7 it is.
I think we can round it off to 14.7.
You can
Fair
say
enough.
a pressure of 14.7 psi is equal to the weight of the column of mercury at 29.92 inches. The expression inches of mercury that you hear the weather forecasters always use thus becomes an expression of pressure and can be converted to pounds per square inch or psi. 29.92 inches of mercury divided by 14.7 psi equals 2.036 inches of mercury per psi. That's often rounded to 2 inches of mercury per psi, and that's typically used for the conversion. PSIA, or pounds per square inch absolute, accounts for the 14.7 psi of standard air pressure and is the pressure measured relative to a full vacuum. The pressure of a vessel void of any air molecules is designated as 0 PSIA. So what is vacuum? We'll take a close look at the vacuum range on this vertical scale of pressure. And that is what occupies the space below atmospheric pressure. PSIG, or pounds per square inch gauge, is designated as pressure measured relative to the air pressure of the surrounding environment. At sea level, 0 PSIG is equivalent to 14.7 PSIA. We've talked about vacuum now a couple of times. So what is it? Vacuum is defined as space void of any matter, almost impossible to achieve.
Very, very difficult.
In the refrigeration industry, it is an expression defining the pressure range between Earth's atmosphere and no pressure. It is usually designated as inches of mercury vacuum and abbreviated INHG with the reference to vacuum along with it. And you can note here, 0 PSIG right here is equal to 14.7 PSIA.
Correct. PSI absolute.
And 29.92 inches or 760 millimeters of mercury vacuum is equal to 0 PSIA.
Correct. And it is impossible to go below 0 PSIA. That is not physically possible to do.
Fair enough. What's heat? We said refrigeration is not cooling, but that it's the transfer of heat from a place that you want to be cooled or cold or frozen to a place where, shoot, it's hot.
Mm-hmm.
How does that happen? Now you got to keep in mind that refrigeration is not cooling, but rather the transfer of that heat from one space to another via a medium that we typically refer to as a refrigerant. You commonly hear it called, what, Freon? Everybody wants to call it Freon, but
correct.
That's a trade name.
That is a trade name. That is not, it is a refrigerant, and that's something that I'm mildly familiar with.
You know a little bit about that.
A little bit.
Okay, we don't have an hour and a half for you to tell us what you know.
Darn it.
Yeah, that would just be a start. Well, what is heat anyway? Heat is the form of energy that is transferred between two substances at different temperatures. Following the laws of physics and thermodynamics, more specifically thermodynamics, the flow of heat is always from a substance at higher temperature to a substance at lower temperature. Well, if that's the case, how do we get something that's cool, colder, or frozen when we're trying to move the heat to a place that's warmer? That doesn't make sense unless it's acted upon by some outside influence. What might that be, John?
Well, that would probably be an increase in pressure via shaft work done by the compressor.
Oh, now we're getting complicated. Well, another way to think about refrigeration is as a process for moving heat from a place where you don't want it to a place where it's tolerable. In the refrigeration industry, heat is often expressed in terms of British thermal units, or BTUs. According to Refrigeration Basics, 12,000 of those little boogers per hour equals 1 ton of refrigerating capacity. We got a little more on BTUs on this next slide. Let's examine BTUs in greater detail. A British thermal unit is a basic measure of thermal or heat energy. 1 BTU is defined as the amount of heat energy required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. It's usually, we're talking about water that would be at its most dense conditions, I think is how that's defined.
Yes.
BTU per pound, abbreviated BTU/LB, is an expression of heat energy content per unit of mass of a given substance. Some people also talk about that as being enthalpy, and in part 2, we'll talk a lot more about that. BTU per hour, abbreviated BTU/HR, or sometimes simply BTUH, is a measurement of heat energy transferred per unit of time. John, why do the British get all the credit on this particular parameter?
Well, it's probably because there was a plethora of British scientists and physicists about the time that this unit was invented, shall we say,
Yeah.
or identified, that were working in the area of thermodynamics.
And they got the credit for it.
Easy for me to say.
Yeah, I see how that goes. Something that sometimes gets interchanged, you'll hear folks talk about BTUs when what they're really meaning is BTUs per hour in a rate standpoint.
Correct.
While those aren't interchangeable.
They are not.
That was slide 13, if I'm not mistaken. Beyond BTU, there are other refrigeration terms related to heat, such as sensible heat. Sensible heat is heat that is absorbed or rejected by a material, which results in a change of temperature of the material. Latent heat, sometimes referred to as hidden heat, is heat that is absorbed or rejected by a material, which results in a change of physical state or phase change of the material. This phase change occurs when the material remains at a constant temperature. That's water to ice, water to water vapor, boiled all the way off.
Correct. Also known as the latent heat is also referred to as heat of fusion.
Oh,
or heat of vaporization.
look at that.
Hey, looky there.
Latent heat of fusion is the quantity of heat described in BTU per pound required to melt 1 pound of material from the solid phase into the liquid phase, or freeze liquid into 1 pound of solid material. The latent heat of vaporization is the quantity of heat described in BTU per pound required to change 1 pound of material from the liquid phase or condensed vapor into 1 pound of liquid. That's pretty neat.
It is, indeed.
That's really special, I think. But what's saturation temperature? We really haven't talked much about that yet. That's the temperature at which a liquid starts to boil or a vapor starts to condense. The saturation temperature, the boiling or vaporization temperature, is constant at a given pressure and increases as the pressure increases. And a liquid can never be raised above its saturation temperature. Water boils at 212 degrees.
At 1 atmosphere.
And if you want to raise the temperature of the water, you'd have to increase the pressure on
Increase
it.
the pressure, absolutely.
Like I got to go to Walmart and buy a pressure cooker.
That would do the trick, yes.
Likewise, if I go up into a high altitude in the mountains, what happens then?
It's going to boil at a lower temperature.
Oh gosh, now I can't cook the hot dogs worth a darn at that point. Can't boil them.
It takes a little bit longer if you're in Leadville.
Darn. Whenever a fluid is present in two states, and I don't mean like Missouri and Kansas, I mean like liquid and a vapor, either boiling or condensing, the fluid mixture will be at the saturation temperature. When water is placed in a kettle and heat is applied, the sensible temperature will rise until it reaches the boiling temperature, 212 degrees at standard atmospheric conditions. While boiling, the temperature will remain constant as long as the pressure remains constant and as long as we're talking about a single molecule of substance. The kettle here contains both liquid water and water vapor, and it boils at the saturation temperature corresponding to the pressure which exists in the kettle. It looks like you've just concocted a still here, John.
It kind of does.
If the water vapor exiting the spout of the kettle is passed through a coiled copper tube where the heat, which has been absorbed during the boiling, is allowed to transfer through the copper tubing, as the heat escapes from the water vapor, it condenses back into liquid water. I don't think Tito's has got anything to worry about from us here.
To be clear, this is just water boiling in here.
Okay,
it's not anything else.
It's not grains or anything.
No, it's not any kind of sour mash or
just
anything
so
like
everybody
that.
knows,
Just
we're
so
not making
everybody's
whiskey or
correct.
Tito's or whiskey would have to be aged in barrels.
It would,
right now,
yeah.
so no problem there.
Yeah.
Both water vapor and liquid water are present in the saturated mixture is at a pressure which corresponds to the atmospheric pressure which exists at this point. When liquid water droplets emerge from the copper tube, they will be cooled to a temperature well below the saturation temperature corresponding to atmospheric temperature. At that point, you could maybe talk about the water being subcooled. In a similar way, whenever a refrigerant is present in two physical states, liquid and vapor, in a refrigeration system, either boiling or condensing, the refrigerant mixture will be at the saturation temperature which corresponds to the pressure in that part of the system. Refrigerant liquid boils in the evaporator section at a low pressure, which allows the saturation temperature to be below the temperature of its surroundings. Heat transfers through the tube and is absorbed into the refrigerant as it changes state from a liquid to a vapor. Refrigerant vapor changes state back into a liquid in the condenser at a high pressure. The saturation temperature of the refrigerant in the condenser is above the temperature of its surroundings. Heat is rejected as the change of states occurs from a vapor to a liquid and is transferred through the tubing to the cooling medium in the condenser section. That's how we get the heat to run uphill.
That's how we get the heat to run uphill, absolutely. That's how we transfer heat with a refrigeration system. And sometimes we can be interested in the cooling effect. Sometimes we can be interested in the heating effect. But that's how it works. That's the fundamentals of how it works.
There's a couple other points here that are worth discussing. One is superheat, one is subcooling. Superheat is a term which describes a vapor temperature rise above the saturation temperature at a corresponding pressure when heat is applied to a pure vapor in absence of any liquid. It's probably a good point to make that the refrigerant discharging from the compressor here would also be in a superheated state.
Indeed, it's even more superheated than that going into the compressor.
Yeah. Now in the condenser, the refrigerant is being condensed and it's rejecting heat to this high temperature ambient. And if there's enough capacity built into the condenser, what do we have here?
We have subcooled liquid.
Subcooling is a term which describes a liquid temperature
when it drops below the saturation temperature at a corresponding pressure. That happens when the heat is removed from a pure liquid in the absence of any vapor. So that is very similar to what we just illustrated with having the steam out of the copper coil that looked an amazing lot like a still, but was not a still. By the time the water drops out the end, it is now subcooled. Those are the two main concepts when we talk about this change of phase. We need some superheated vapor going into the compressor because compressors do not like liquid in any way. They do not like liquid refrigerant. We're going to have superheated vapor coming out of the compressor, and we need subcooled liquid going into our expansion device because most expansion devices really prefer to have all liquid coming into them. And so those are two things that we focus on in the world of refrigeration, just as basic system operating necessities in order to make the system function correctly, reliably, and lead to its better longevity.
And we'll get into more of that in part 2 when we discuss that.
October 1st,
Yeah.
right?
Yeah, we had a comment that was posted with regards to this diagram that said we might have mislabeled this. Remember that?
I do remember that. But the diagram is indeed correct. We do have subcooled liquid coming out of the condenser and headed toward the expansion device. And we do have superheated vapor that would be coming out of the evaporator We could also draw an arrow from that superheated vapor up to the line in between the compressor and the condenser. That is also a superheated vapor. But typically when we're talking about superheat, we're talking about that area right there, the suction line coming back from the evaporator to the compressor.
Now would be a good time, if you have any questions that would be pertinent, you can type them into the Q&A window. Do we have any questions we ought to deal with at this point, John? We're in pretty good shape from a time perspective.
I believe that we have one. Let's see here. We have what are the different ways to transfer heat? If the fan is blowing air over a coil, that is one form of heat transfer. What are the others? Well, typically in the types of systems that we're talking about, we typically do have air coils. So we do have a fan blowing air over a coil, and we have tubes and typically fins that would transfer the heat to or from the refrigerant inside the coil to the air. But there are also others as well. You have sometimes plate type heat exchangers where you're typically using two fluids, or you are using one side as an evaporator and one side as a condenser.
Yes.
So that is basically, I guess you could say that the mode of heat transfer that we're showing here with the fans, that's mainly convective heat transfer.
Convective, and then you've got the effect of the sun radiating upon us. That's
radiative heat transfer. But if we look at something like a plate type heat exchanger, then we might consider that conductive heat transfer.
fair enough.
But there's a little bit of all of those. There's a little bit of convection and conduction going on in all of them.
Okay.
So that's the way I would.
All right. Any other questions that you think we ought to handle at this point? Are we in good shape?
Right at the moment, no. I think we're in great shape.
Well, just so you know, as a reminder, Sporlan is always here to assist you with your air conditioning and refrigeration flow control needs. You can reach us by calling 636-239-1111. That's our general number. That'll help get you to customer service or tech support. You can also dial tech support directly at the number provided there, 636-392-3906. And we're always available 24/7 at sporlan.com, which is a resource for product literature, virtual engineer, our product selection program, and a whole lot more. You can even view an encore performance of this webinar on Facebook or YouTube. It'll appear on Facebook first and on the YouTube channel a little later. Eventually, it'll be out there for you to view again and again, or for even the first time. And it's simply a reminder regarding the next two webinars. September the 17th, we'll finish up methods of temperature control with the electric evaporator pressure regulator. October 1st, we'll do part 2 of what is refrigeration. Please join us for these informative and fun webinars. And I tell you what, if John Woodhouse is here, it's going to really be fun.
Absolutely.
And this concludes our webinar on what is refrigeration part 1, Chill Skills Training Module. Please join us next time.